And many of those tools that you saw, for example, ParElm, that is able to remove unused parameters, they also use these axioms to justify the validity of sound. So they could be useful. Before you go to model checking, you could reduce your specification quite a bit, and then perform model checking on the reduced state. Shall we wait for those who left? I think 2 left now, right?
She came back.
She will come back. So maybe I'll wait for a couple of seconds. So I suggest we start because we're really short in time. I would like to talk about axioms for parallel processes, okay? And we have seen some introduction to parallel processes. You know how their state space is generated. You have seen these diamond structures. You also have a flavor of the difficulties in axiomatizing parallel processes. So I will quickly go through those steps just to recap what you've seen before, and then give you the axioms for parallel processes. Calculate a very simple example. I hope we will be done in 15 minutes or so that we can go to the coffee break. So just to remind you, this is the semantics of a parallel composition. You could, either the left-hand side can make a step, independent step, and then the result is updated in the parallel composition. Or the right-hand side can do the same. Or they synchronize and the result is a multi-action, right? So that they do an action at the same time. And as I said, this is very peculiar to MCL2. Most other process algebras do not have this concept of multi-action, which has its roots in something called true concurrency. So true concurrency means that you do 2 things really at the same time, right? Most other process algebras do not allow for multi-actions and do not model this. I think one of the motivations, and Jan Friso can confirm, behind this is that MCL2 was designed to kind of consolidate process algebras with Petri nets. Petri nets do have true concurrency semantics, and MCL2 was designed to be able to model Petri nets as well, and this concept of parallel composition is capable of modeling these type of true concurrency stuff, right? This was an example of a parallel composition where you had A followed by A in parallel with B followed by B, and then you saw all sorts of diamonds all around, and we solved another exercise yesterday. And if you recall, I asked you yesterday whether this is a sound axiom with respect to strong bisimulation, and the answer was no, because this one allows us to delay our choice by first taking a Coke, and then later deciding whether we want to go for dish 1 or dish 2. While here, the first action, no matter whether it's dish or Coke, will resolve the choice, basically. Then we don't have any choice anymore, right? And as I said yesterday, this was given as a problem to Farron Moller, who was a PhD student about 20 some years ago, with Robin Milner in Edinburgh. And he was studying whether he can come up with an axiomatization, as you saw, a finite axiomatization of process algebra with parallel composition, right? So Milner couldn't do that. Milner, in his original book, wrote a rule scheme, which actually stands for an infinite number of rules, an infinite number of axioms. And then he asked probably Farron Moller, I don't know whether he really asked, but that was the subject of Farron Moller's thesis, whether Farron can come up with a finite axiomatization for process algebra with parallel composition. And Farron Moller came with a very intricate proof. It was published about 25 years ago in ICALP. ICALP is one of our main conferences. So if you want to know whether a result is really good or not, then you should look at, for example, Concur, which is the main concurrency theory conference, right? Then we have LICS, Logic in Computer Science, ICALP, and these are kind of flagship conferences for our community. And Farron Moller published this paper in ICALP, I think, 1985 or something, or maybe 91. I don't remember the exact year, where with a very difficult, intricate proof, he showed that parallel composition cannot be axiomatized using finite number of axioms. I spent about a year of my life understanding his proof and also trying to redo the proof for timed CCS. So he did it for CCS. I tried to do it for the case with time. And it turned out that this is a completely different proof. So we eventually proved that timed CCS cannot be axiomatized either. but there are all sorts of complications arising from the addition of time to CCS. But these type of proofs are intrinsically very, very difficult. If you're interested, I can give you some interesting open problems to have a look. But you really need to spend days and nights thinking about the proofs and trying to figure out the details. They're very interesting stuff. I must say that I am not anymore very enthusiastic about them because their practical implications are very limited. So it doesn't really matter whether you can have finite axioms or infinite axioms as long as you have an algorithm to transform the processes. So I tend to think in the hindsight that this is very interesting theory, but with very little practical implication. Anyway, so he showed that you can never axiomatize parallel composition using a finite number of axioms. And this is a really brilliant result. And since then, there is a whole industry of reproducing these type of results for different types of process algebras. Then Jan Bergstra and Jan Willem Klopp came up with the idea of axiomatizing parallel composition using two auxiliary operators, and I need to explain them before I show you the axioms. So the first auxiliary operator they introduced is called left merge. It's exactly like a parallel composition with the difference that it dictates the first move to be made by the left-hand side process. So it's exactly like a parallel composition, but the first move has to be taken by the left-hand side, and then it evolves to a normal parallel composition, right? So P left merge Q will evolve into something else. If P can do the first step, and then the result becomes a parallel composition of the result of the evolution of P in parallel with Q, right? So it immediately becomes a parallel composition as soon as the first step is made by the left-hand side process. Is this clear? So what do you think this would be, for example? This is deadlock, right? Because it first requires this one to make a move. Since this one fails to make a move, the whole thing deadlocks, right? What is this? Yeah, this is first doing an A. So it will first do an A, right? It will become, for example, 0, something that has terminated, epsilon, whatever, in parallel with B. In parallel with B. And this can only do a B, and then it will become epsilon parallel with epsilon, right? So it will be AB. It is equal to, similar to AB, right? Just one more example to make sure that we understand everything. What is A, B, C, for example, or B plus C, even better? It's A dot B plus C. And if I put here B dot C, it will be A dot B dot C, right? So nothing complicated, right? Okay. So this is left merge. And then communication merge is exactly the same. The only difference is that the first step has to be taken simultaneously by the two sides of the communication merge. So both P and Q should evolve, and then the result will be again a parallel composition, right? So again, to make sure that we understand the concept, this should be killed. There is no trash bin. So what is A communication merge B? Right, but assume that we haven't defined it, it's just a multi-action, right? So it's there is the same notation for communication merge and multi-action. Communication merge of A and B is the multi-action A with B. What is this? It's deadlock again, right? So because you need to take both actions from the two sides. Since this one fails to make any action, then this one also deadlocks, right? Is this clear? Then, as soon as we add these two operators, so there is an interesting proof, I think also due to Bergstra and Klopp, that you can never axiomatize Is there a proof? Now I wonder. I have been working myself on this proof, so I wonder whether this is there or not. I will make the statement and then Jan Friso can help me. I strongly conjecture, and I don't know whether there is a proof for it or not, that you can never axiomatize parallel composition using a single binary operator. And I don't think there is a proof for that in the literature. That's something I worked on for some time and I gave up.
There is no proof that you cannot
Axiomatize parallel composition with the addition of just one single auxiliary binary operator. I don't think that exists. Okay, so I conjecture very strongly that there is no finite axiomatization for parallel composition with a single binary operator. And I don't think there is a proof of this in the literature. I think if there is a proof, or if there comes a proof in the future, it will be very complex. I think we have a draft, mostly due to Luca Aceto, of about 50 pages to show this, and I don't think we have the proof yet ready. I think it's far from a complete proof. Right? So with none of these, and with no other binary operator, you can axiomatize parallel composition. And I don't think this has been proven ever.
I do not know, but I have the tendency to try to prove it now. But that's
You could do that. But to the contrary, if you look at ternary operators, it's very easy to cook up a ternary operator that can axiomatize parallel composition. So with a binary operator, you can never axiomatize parallel composition. This is a conjecture. This is not proven. But with a ternary operator, it's very easy to do it. You could basically combine left merge and communication merge and then axiomatize parallel composition. But anyway, suppose we add these two, then it's very easy to axiomatize parallel composition. The first axiom that you add is that P in parallel with Q is nothing but P left merge Q. So either the first action is taken by P, or the first action is taken by Q, Q left merge P, or they synchronize. Okay? That's what parallel composition is. So we haven't done anything new. This is easy to prove that. This is easy to prove sound with respect to strong bisimulation. Basically, it's saying if you have a parallel composition, it cannot be anything else but first taking an action by P, or taking an action by Q, or synchronizing on the common multi-action of P and Q. That's very sound, very intuitive, right? Yes?
Intuitively, what is the thinking behind these kind of proofs? Which methods do they use?
For soundness, it's basically constructing a bisimulation relation. So when two processes are bisimilar,
No, I meant for the axiom, when you said that there is an axiomization with only one binary operator.
So it's long ago when. So if you go back to Farron-Muller's proof, that showed that parallel composition cannot be axiomatized. It's a very intricate induction on the structure of P and Q and a lot of case distinctions. So I think you need to consider, I don't know, 20, 30 cases based on what is P, what is Q, and then in each case show that if there were a finite number of axioms, you would equate two processes that should not be considered equal, because your axiom should have a certain syntactic shape, and that syntactic shape can equate more processes than necessary. Right? So you basically count the number of terms. You know that you can always reduce terms to a certain normal form using the sound axioms that you know from parallel composition. So even if you have a infinite number of axioms, you know how the normal form of process will look like. So you should be able to reduce all processes to this normal form using a finite number of axioms now. You postulate something about the shape of those axioms, and then you show that no matter which shape you take, you would equate more than necessary. So you find you can prove two processes bisimilar that should not be bisimilar. It's a very difficult proof. As I said, I think Farron-Muller's proof is easily 5-6 pages if you write it down properly, and in many cases it's like tens of pages for other process algebras. So there is a very nice paper by Luca Aceto. It's called The Saga of Axiomatization or Axiomatizability. Axiomatizability of parallel composition, something like that. By Luca Aceto. And he gives a nice historical account of all these results in the literature. Yeah. Saga, S-A-G-A. Good. Now, so the first step is to rewrite parallel composition into left merge and communication merge. But left merge and communication merge have a very peculiar property. Namely, we saw in the past slide that plus does not distribute over parallel composition, right? Plus does not distribute over parallel composition, while plus does distribute over both left merge and communication merge. That's a very interesting result, right? So I will show it to you in the next slide, but I would like to emphasize it here. So we know that P plus Q parallel R is not bisimilar to, no, sorry. This does not hold, right? While, interestingly, this does hold. So P plus Q left merge R is equal to P left merge Q, left merge R plus P left merge R. No? Q left merge R. So plus does distribute over left merge. Intuitively, why is that the case? Because the first choice has to be made by this side. So as soon as you do an action, you do resolve the initial choice, right? On this side, the same. As soon as you do an action, the action has to be taken either by P or Q, and the first action will resolve the choice. So intuitively, this is a sound axiom with respect to strong bisimilarity, and you can show it using a very simple proof that this is indeed the case. Likewise, this, and I make the same mistake over and over. This is also a sound axiom. And this is the crux of parallel, axiomatizing parallel composition. So you first rewrite parallel composition. No? 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 You first rewrite parallel composition into left merge and communication merge, and then you push the choice inside more and more until you get a normal form of processes. So in particular, if you have dish 1 plus dish 2 left merge coke, then you have to choose the dish before you go for a coke, right? So that's why it does distribute over a left merge. Likewise, if you have to choose them simultaneously, basically you have to make the choice initially as well, right? And here is the full axiomatization for parallel composition. So the first step, as I said, is this rewriting of parallel composition into left merge and communication merge. Then you have the axiom that I actually showed you before. If you have an action or multi-action left merge with X, then the result is basically sequential composition because you have to take the first action from the left-hand side, right? If you cannot do an action on the left-hand side, then you deadlock. If you can rewrite the left-hand side into an action or a multi-action followed by X, left merge Y, then this will be kind of factored out, right? You can factor out alpha, and the result is a parallel composition again, right? If you have a choice, you can distribute choice. If you have a sum, you can basically distribute the sum over. So then the order of parentheses is basically like this. Is this clear? So, and then a similar set of axioms are there for left merge. For communication merge is commutative. It's associative. The order of parentheses does not matter. If you have a tau communication merge with X, you get X. If you have deadlock, you get deadlock. If you have a sequential composition, then you can factor out the multi-action, and then the rest will follow, right? Likewise, you can factor out, and the rest will be a parallel composition. You can distribute choice, and you can distribute sum over left merge. Okay? Let me give one example, and then I will conclude this lecture. Okay? So suppose I want to A dot 0 in parallel with B dot C dot 0. What should be the outcome? If I want to rewrite it into a sequential process, could you help me? So either the first action is taken by this side, and then I obtain. If the first action is taken by the left-hand side, what should be the outcome? Exactly. Then the rest will follow. A dot B, sorry, dot B dot C dot 0, right? So the first choice is to take the first action by this side, right? If the first action is taken by this side, then I first do a B, and then what will follow? Right, so then I have A dot 0 parallel with C dot 0, but then I should rewrite that into so either I have A dot C dot 0, or I have C dot A dot 0, or I have A, C as a multi-action dot 0. Everyone agrees? So if this first action is taken by this side, then I have the parallel composition of A and C, and intuitively that's the parallel composition of A and C. Right? Finally, if they do the action together, then I have A multi-action B followed by C followed by 0. Right? I want to prove this using the axioms that I showed you. Oops. Okay, I start from this side. I will rewrite it to this side. What is the first axiom to apply? If I start from here, which axiom should I apply first? M, right? M is the first axiom that is applicable. So I start from this side, A, B, C, 0. If I apply M, what do I obtain? Parallel composition will be rewritten into left merge, or the other way around. So BC0 left merge A, or communication merge A0 BC0. Everyone agrees? Okay, now I want to rewrite this one first. What axiom shall I apply? LM1 is not really applicable because I have a parallel, I have a sequential composition here. LM3, right. LM3 tells me that I obtain A dot, and then I have, oh, I wrote 0. By 0 I mean delta, right? So let me rewrite this to delta. That's easier. Okay, so I have A dot followed by, can you help me? I'm rewriting this term. Right. LM3 I'm applying. Parallel. Exactly, parallel, and then B dot C dot delta, right? And then the rest will remain the same. Because we are quite short in time, I will only rewrite this as soon as I obtain this, then I'll stop, okay? Okay, how can I rewrite this further? What should I apply here? M. Very good. How can I apply m? I can apply it on the innermost term, right? A dot, and then what will come here? Either left merge of delta with the rest, or swapped, right? B dot C dot delta left merge delta, or communication merge of delta with B dot C dot delta. Right? Now let's focus on this one. What axiom does apply here? LM2, very good. So we get A dot delta plus B dot C dot delta communication merge delta left merge delta B dot C dot delta. Everyone agrees with this? So I just rewrote this term using LM2 to delta. Yeah? Now let's focus on this one. How can I rewrite this one? B dot C dot delta left merge delta. What axiom should I apply? LM1 does not apply here because I have a sequential composition. What axiom does apply here? LM3, very good. So I have A dot delta plus, and then if I apply LM3, I will obtain B C delta left merge delta. Sorry, parallel composition delta. Let me rewrite this one also right away. Which axiom can I apply to rewrite this one? S4, yes. So plus delta. Maybe you remember what was x plus delta? X, right? So I have x plus delta here. That will be B dot C dot delta, and then plus delta again, right? So then the whole thing will be this, right? So let me rewrite this. A dot B dot C dot delta parallel composition delta. Everyone agrees with these steps so far? Now, how can I rewrite this one? Of course, there is more here. I don't remember what the name of this axiom was, but it doesn't matter. How can I rewrite this one? What was your suggestion? LM? No, I have parallel composition. So the only way to rewrite parallel composition is using M, right? I have A dot B dot either C lambda left merge, C delta left merge delta, or delta left merge C delta, or C. Right? Everyone agrees with this? So I'm rewriting parallel composition into left merge of one side with the other, or swapped, or communication merge. I could quickly do a trick here before I go further. Communication merge is commutative, right? So I could rewrite this immediately into right? I could just swap the two sides. It doesn't matter. Okay? Now, I want to rewrite them one by one. I start from this one. LM3. Very good. LM3. And of course, there are other terms that I haven't rewritten. And now I run out of a space, so what should I do? I should use the other whiteboard. Thank you. Oops. I think this is good. I hope it doesn't block the screen. Okay. So if I apply LM3 there, what do I obtain here? I have A dot B dot C dot delta parallel delta plus, and then I should apply. So with LM3, I reduce this one to what I wrote. What axiom should I apply to reduce this one? LM2, right? LM2 says if you have delta on one side, on the left-hand side, then you obtain delta. So I apply LM2 here, and thereby I obtain delta. Last one, you need the next page. S4. So let's apply S4 there. What do I obtain here? No, delta. You agree? I had S4 says, oh, no, that was my mistake. Yeah. So I apply this to rewrite this into C dot delta parallel with delta, and then I apply S4. What do I obtain? Delta, right? So I have X plus delta here. What should it be? C dot this. Again, X plus delta. So this whole thing is A dot B dot C dot delta in parallel with delta. How should I rewrite this? M again. So by applying M, I get A dot B dot C dot You agree? X plus X is X plus X, X plus X, X. So I obtain this, right? How can I rewrite this further? LM2, right? So I obtain LM2. I obtain A dot B dot C dot delta plus. And then I need to rewrite this one. I apply here S4. I obtain delta. Delta plus delta. You could either use X plus delta is X or X plus X is X. That's delta. So this is equal to A dot B dot C dot delta. Okay? So that's the first summand here. If I correct this here. I have obtained the first summand here. Then I need to apply axioms on the second summand over here. And then I should obtain this one. And the third one, I should obtain this one. Okay? You see, this is quite cumbersome. You don't want to do this by hand. That's exactly what will happen if you linearize the process. So when you write a parallel composition, then all these axioms are applied automatically. And then you can immediately see in LPS file a similar structure as this one. Of course, this is not yet linear, so what will happen is that you obtain, with the first equation, x is equal to a y, and then y is b z, etc., etc., all right? But this essence of linearizing, sequentializing a parallel process is implemented in the linearizer tool. Right? Any further questions? So let's take a break of 15 minutes. We reconvene at 3:15. Okay?
This is a smart home system problem with a user and only one device. It's a lamp. If it is the controller, we have two actions from user. Yes, user lamp on, and user lamp off, and another action is when we want to read.
What do you want to read?
Reading.
Oh, read, just like a book.
Yes. And there is a lamp. Yes. And there is a maybe internal action. Yes.
So what is that? What is that that is connected to
A lamp. And
For the controller, that is an external action.
external
The
action.
internal actions are really inside the controller.
Yes.
The
This is
external,
outside this.
so the lamp is really outside the controller. So
Yes.
switch the lamp on is a external action.
And two input from sensors is day or is night. They translate to two actions. Yes, and the requirements are: if user switch on the lamp and it is night, it is day, if the user switch on the lamp, but it is daytime, the lamp stay off. Yes, and if the user switches on the lamp and it is night, the system switches on the lamp.
So I think that the first requirement can be even more abstract. Namely, during daytime, the lamp will never go on. So you can,
Yes.
in fact, that's a more concise requirement and therefore nicer than the one you have. And I think that was also the one we checked.
Yes. Yes.
During
During.
daytime, the light will not be switched on because we want to save energy.
Because of energy saving. This is the MCR2 program. These are actions: user lamp on, system lamp on and off for system and user, and then is day and is night, and read. In procedure, we said that we have a parameter time, day or night, and when the time is night and user switches the lamp on, when it's night and switches the lamp on, the lamp on. Yes. Yes. But if it is day and user switches the lamp on, it's still remain off because the requirements are requirements. Yes. And if it is night and user switches the lamp off, it remain on? No. It remain on? No, it's yes. It should be off. If it is day and user lamp off, the lamp remain off. But if it is day and lamp off in day, it is another branch. Yes. If the user wants to read and the time is night, then system switches the lamp on. Yes. Otherwise, the lamp off in the daytime. Yes. And something like this for lamp on. The main notion is that when user wants to read and it is daytime, there's no need to switch the lamp on. But in nighttime, the system automatically switches on the lamp. And this is our, I think this is our property. Yes? Our property. Yes? Box true star and is there?
I think we're open in another window in the same thing. If you go to M0 to XC, if you go back to the integrated and your XC file.
Uncertain. Box true star and is day and not during night. Yes. Then system lamp on and then false. Yes. This means during the daytime lamp cannot be switched on. Yes. And then
This is a function that uses.
I'm sorry?
This is a function that uses the other side.
This
is a function that uses the code.
No, this is the new calculus property, and she wants to verify on the LPS of the model she made. So she first made a model, she wrote that property, now it's translated into new calculus. Now she can verify on the LPS.
Then I make the LPS from integer 2 and then transform it to PBS. Yes. And
At first we model some things, then the requirements translate it into new calculus and check it with the model.
What you could also do was to hide some actions that are not relevant for a particular property, and then reduce the state space modulo, for example, strong modulo branching by simulation or modulo traces, and then you get something very small, which you can inspect using LTS graph. So you can look at it and see whether it looks intuitive or not. Right? Each property mentions a couple of actions. So is they, for example, have light on, right? So you hide everything else, but is they have light on. Then you reduce this, you regenerate the state space in this more abstract model. Then you reduce it modulo branching by simulation, and then you get something very small with a few transitions, a few states. Then you can inspect visually, just manually, whether it satisfies the property.
Daylight, MCF, yes.
Maybe you should say it again. You just say it.
Yes. And LPS, yes.
It's an error, but
LPS to PBS.
I do think that the path is not correct here, so maybe you should browse and then find the file at the right time.
Yes.
So you go to desktop, and then M02, and then this.
The last one.
Yeah, now you're on.
Yeah.
Oh, it's an error. Are you sure you saved this?
Yes.
Double click maybe?
Yes, this is
Okay,
false.
but this is okay. I mean, the idea is clear. I don't know why it may not work. Let's just make it work. That's fine. For some reason, they didn't earlier. I don't know what. So maybe you want to say something more what you want to do with this model. So what is the goal of this case study in the future? How do you want to extend it? What do you want to do with this?
I want to extend it with more devices, something like Windows, mixed initiative Windows, and blinds, and then detect the conflict between the user action and system action.
So I think the next step would be to model those devices and model the possible interaction of the user with those devices. And then we can formulate possibly conflict as a model view calculus formula. And then check and detect some possible conflicts, and this is how we can solve them by, for example, adding more monitors that interact with these devices. Any questions? If they don't need. Do you know whether she left? Okay, thank you. I think this is very nice.
Let's take 5 minutes, which will be a little bit more than 5 minutes, to say a few last words, because we're coming at the end of the day. But I will be here until 7:30. So if you would like to continue working, I will be available. After that, we have to move around somewhere. And tonight, well, tomorrow morning at 6 o'clock, I will be back in the Netherlands, so I can start to work at 8. Whether I will then be awake, that is another question. I think we looked at the very basics of modeling, and I see that everybody of you have some basic modeling. We even saw some verification. We are not, I had hoped that we could have been a little further, but I think it's quite time consuming to actually learn something. But if you finish these basic steps, so I think the stage where you are in, you have seen all the essential elements, and that means that from this point on, it's of course acquiring more skill, but you should just extend your model. You will not see anything from the language itself which is new. Well, tiny things maybe, but so the essentials are really shown. What I think is that if you like to continue this modeling, and you have a model and you would like me or Mohammed to look at that, then I think you can send us the model, and we can also comment and help you if you have still some difficulties with writing down the properties. Yeah, it's not easy to start, but if you get the hang of it, then all of a sudden I think you can accomplish quite a lot, and that's also what the toolset allows you to do so. And I think there is quite a lot of reading material, so if you look in the book, especially to the first chapters regarding modeling, but also to the other chapters, you will find quite a lot of theory on how to actually translate to p-bases, how to solve p-bases, how to express bisimulation in p-bases, how to reduce in smarter ways your linear processes. There's much more. I would like to just mention two extensions which we find important at the moment, and I would like both extensions to be as powerful as the current, say, process algebra. And one is about time, and that's already part of the language for quite a while, but I will shortly indicate how you specify timed processes, just to get that you get the feeling that it exists. For the time being, actual timed verification is still hard. We are still working on that, and we may need some help. So if people have ideas on how to really do this, then that's absolutely interesting to work on. So up till now, we saw single actions like this, and single processes like sometimes indicated as a variable or sometimes indicated as a process P. And these are actions or processes that can take place at any time. And we are only interested in doing an action at some point and then an action after that, but we are not really knowing what the precise time is. You can also model time by, for instance, having tick action and saying we have an A and then a tick and a tick and a tick and then a B, and then these ticks represent, let's say, a second passed. But you can also do it very fundamentally. You can say A and then, for instance, 3. And this means, this symbol here in the tool, it is written like this: A, monkey tail 3. This means A happens at time 3, being followed by A happens at time 4. And this is the only extension that we have in the language for time, but it allows us to say that, for instance, A happens in an interval. How do we write that down? Well, we can say we have a timed variable of sort real. Let's suppose we want to say A happens between 3 and 4 seconds, then we say T should be between 3 and 4 seconds, and then we can speak about A at T followed by a further process. In this way, by putting these conditions here, well, in the tool you should write 3 smaller equal T and T smaller equal 4, we can actually indicate that during this whole interval, this action A can happen. One of the problems is that you cannot generate a state space anymore because you now have an uncountable number of transitions between 3 and 4. But then there are tools like LPS untime and LPS real elm. Some of them you find in the experimental tool sets. And in certain cases, these are quite capable of removing the time, but after which you can generate a finite state space which still represents exactly the behavior of the timed processor. So that is available there. A company like ASML at this moment told us that they really want us to be able to do timed verification because they want to squeeze every millisecond out their performance, and they want to exactly model and understand the timed behavior of the system. So this is one. And there's one other development which is interesting and which you may find intriguing, which is currently under development, and that are probabilities. And probabilities allow you to say that you can actually choose a particular variable with a certain probability, and then you can model non-determinism and probabilities inside the same framework. And you will find that if you look into the tool, it's not very, we did not make that. Can use this also, can generate state spaces with it. You will find a paper on my webpage, very recent paper with examples with probabilities. And what you basically do is, for instance, if you would like to throw a coin, you say, I have a distribution where I take a Boolean where you can get true with probability false, probability and a half, and false with probability and a half. Here you write your distribution, and then you can write down if this is a process, if B holds, then you do head, else you throw tail. And if you can model these kinds of processes, then you can combine also parallel processes with probabilities. You can generate state spaces. We, at this moment, implemented a very fast tool to do strong bisimulation reduction, but we do not yet, that's all research going on, have a branching bisimulation reduction, and we are working on extending the modal formulas, also such that they work in probability. So this is all showing what's currently under development, and I hope that the next time I will come back here in Tehran for perhaps a next summer school, that I can say, well, let's skip the also exciting part about modeling just ordinary processes, but let's take these difficult probabilistic systems and let's model these ones. Well, I think that what we can do in the future with this is all quite great. Well, there are many more developments going on. I think the question how to make the tools faster, how to do better verification, how to verify systems with 10 to the power 1000 state spaces, how to get more and more companies involved such that we first make models of software and that they make the software, which is just a little bit reliable, then they can make it today at much lower costs. All these are big issues that we should work on. But let's first get the models going as you are doing. And as I said, if you at some point have the feeling that you have questions, just send me an email and I can see what I can do on a distance. Okay, so I would like to stop here. I quite enjoyed being here. It's always, well, I've been here now 3 times, always really enjoyable to be in Iran and visit all these places and see what it is happening, and it is also enjoyable to give such summer schools. Okay, thank you.